Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll wander through one of the most mysterious frontiers of all. Not the far reaches of the cosmos, but the universe within your very own perception. The senses are your body's storytellers, translating the language of the world into something you can see and feel. They build the illusion of reality from simple vibrations, chemicals, and light, and turn them into the entire world around you. You'll discover how your brain fills in what your eyes can't see, how sound can shape the flavor of food, and how plants themselves can feel the gentlest touch. Every heartbeat, every breath, every flicker of color is a quiet miracle of perception. Before we begin, if you enjoy these gentle journeys, feel free to like and subscribe or share a thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, get comfortable. Let your eyes grow heavy, and let your mind open to the secret symphony that surrounds you every moment of your life. Let's begin. Your brain can reinterpret taste based on what you see. The color and appearance of food can quietly reshape its flavor in your mind. When you see a strawberry yogurt dyed green, your brain may insist it tastes like lime. In controlled experiments, identical drinks colored differently are described as tasting sweeter, sourer, or fruitier, even though they're chemically the same. Vision has a powerful influence over expectation, and expectation, in turn, changes perception. Your brain blends signals from sight, smell, and texture to predict what flavor should be there, and often it fills in the gaps. The act of tasting isn't a single sense, it's a multisensory illusion, choreographed by your brain's guesses about reality. What you think you're tasting is often what you expect to taste. Your mind isn't lying, it's completing the picture. The flavor, in a way, exists as much in imagination as it does on your tongue. Some people can literally taste words or colors. There are rare individuals whose senses intertwine in a phenomenon called synesthesia. For them, sounds may sparkle with color, numbers might carry textures, and words can have distinct flavors: cinnamon, copper, or chocolate. One person might describe the name Michael as tasting like mint, while another says Tuesday feels blue and rough. These experiences aren't imagined. Brain scans show overlapping activity between sensory regions. The boundaries between seeing, tasting, and feeling blur, revealing how deeply connected our senses really are. Synesthesia can heighten memory, creativity, and emotion, allowing people to recall information by flavor or hue. It offers a glimpse into a reality where perception is not separate, but symphonic, where every sound carries color and every word melts on the tongue. In truth, we all experience a faint echo of this blending. The senses were never meant to work alone. They compose the world together. Smell is the sense most directly linked to memory. When a familiar scent drifts by, the smoke of a campfire, the sharp sweetness of rain on pavement, it can instantly pull you back through years. Unlike sight or hearing, which root through layers of processing, smell travels straight to the limbic system, the brain's emotional core. The olfactory bulb connects directly to the hippocampus and amygdala, the regions that shape memory and feeling. That's why a smell can resurrect entire moments with uncanny vividness, not just what happened, but how it felt. Scientists call this the Proust effect, after the writer who described memories rising from the aroma of tea and madeleines. Smell bypasses logic and language. It speaks in pure emotion. It reminds us that memory is not made of images or words, but of sensations, layered whispers of the world, carried quietly through time in the air we breathe. Every human nose is unique, like a fingerprint. Though we rarely think of it this way, your sense of smell is entirely personal. The shape of your nasal cavity, the sensitivity of your receptors, and even subtle genetic differences create an olfactory signature unlike anyone else's. Two people smelling the same rose aren't truly experiencing the same scent. Your unique combination of over 400 smell receptors interprets the chemical cocktail of the world differently, blending notes in ways only your brain understands. This individuality can influence everything from which perfumes you like to which foods you crave. Some people naturally find cilantro fresh and lemony, while others taste soap. A single gene can make the difference. Even identical twins with nearly matching DNA have slight variations in their smell perception. The air carries the same molecules to everyone, but each nose translates them into its own private, invisible language. Your sense of smell can detect over 1 trillion different odors. For years, scientists underestimated our noses, believing humans could recognize only 10,000 scents. But research in the 21st century shattered that myth. Using complex scent mixtures, scientists found the human olfactory system could discriminate between at least 1 trillion unique odor combinations, and likely more. Each smell isn't tied to a single molecule, but to a pattern of receptor activation, like musical notes forming chords. Your brain decodes these patterns instantly, comparing them to memories of flowers, smoke, or freshly baked bread. This immense range evolved because smell once guided survival, detecting spoiled food, predators, or safe shelter. Yet today, it connects us to subtler pleasures. The scent of soil after rain, the salt of the sea, the warmth of another person's skin. Each breath carries an invisible tapestry of information, proof that the world is infinitely richer than we ever perceive. You lose part of your sense of taste when you hold your nose. The flavor of food is a duet between taste and smell, and when one goes silent, the whole song changes. Your tongue alone detects only 5 basic tastes: sweet, sour, salty, bitter, and umami. Everything else, the subtle sweetness of strawberries, the smokiness of chocolate, the brightness of mint, comes from aroma molecules rising up through the back of your throat to your nose. When you pinch your nose shut, you block that passage. The result is a flat, muted experience, where complexity disappears and only simple tastes remain. This is why food seems dull when you have a cold. The moment you release your nose, the fall bouquet rushes in, and flavor blooms once more. Taste, then, isn't confined to the tongue. It's a collaboration between breath and biology, a sensory partnership that reveals how deeply smell defines what we call flavor. The flavor of food is mostly smell, not taste. What we describe as flavor lives mostly in the nose. When you chew, air carrying volatile molecules rises into your nasal cavity, activating the olfactory receptors that truly define the experience of eating. The sweetness of mango, the richness of coffee, the sharpness of cheese, all are aromas, not tongue-based tastes. Experiments show that blocking the nose can make a strawberry taste almost flavorless, even if it's still sweet. Chefs and food scientists rely on this interplay, balancing aroma compounds to sculpt complex flavor experiences. Your brain, meanwhile, blends these sensory signals into one seamless impression. It doesn't separate taste from smell, it merges them into a single illusion of flavor. In that sense, eating is a multi-sensory performance: sight, smell, texture, and memory all performing at once. Every bite is a story your senses tell together, quietly choreographed inside your mind. Some people are super tasters with thousands more taste buds than average. Around 1 in 4 people have unusually dense clusters of taste buds, sometimes twice as many as others. These super tasters live in a world of intense flavor. Bitter foods can taste unbearably sharp, alcohol and coffee can feel harsh, and even mildly spicy dishes can overwhelm. Yet this heightened taste perception doesn't just make things stronger, it adds complexity. Super tasters can detect subtle variations others miss, the delicate bitterness in greens, the depth in chocolate, the nuance in tea. The difference isn't in preference but in physiology. More taste buds per square inch of tongue, each connected to a richer network of nerves. Some scientists believe this trait once offered survival advantages, helping humans avoid toxic plants. Today, it makes dining a vivid, sometimes exhausting adventure. To a super taster, even ordinary food can feel symphonic. Babies are born preferring sweet flavors. From the moment they enter the world, infants show an instinctive preference for sweetness. It's a survival mechanism. Sweetness often signals energy-rich foods like milk and fruit. Studies show newborns relax and even smile when given something sweet, while bitter or sour tastes make them grimace. This early bias helps guide nutrition before learning or experience can shape preferences. Over time, exposure to different tastes rewires the brain, expanding the palate, but that first love for sweetness lingers. Interestingly, the amniotic fluid in the womb carries traces of what the mother eats, meaning a baby's earliest flavor experiences happen before birth. A mother who eats garlic, vanilla, or carrots can subtly flavor her child's world before the first breath. Taste, it seems, begins as a whisper from the outside world long before we open our eyes to see it. Spicy food isn't a taste, it's pain. When you bite into a chili pepper, you are not tasting heat, you're feeling it. The burning sensation comes from a compound called capsaicin, which activates pain receptors in your mouth, the same ones that sense scalding temperatures. Your brain interprets this as danger, flooding your body with endorphins and adrenaline. Yet, paradoxically, this discomfort can become addictive. The rush of endorphins creates a euphoric calm, and with repeated exposure, tolerance builds. That's why spice lovers often crave ever hotter dishes. Their brains chase the thrill. Capsaicin isn't unique to chili peppers. Either mustard, wasabi, and even some black peppers contain related compounds that trigger similar effects. In essence, spicy flavor is a sensory illusion, pain dressed up as pleasure. Your tongue doesn't taste the burn your nervous system does. And somehow, that fiery trick of biology makes food feel vividly alive. Your tongue detects 5 primary tastes, but your brain blends thousands. Taste begins with simplicity. 5 basic sensations: sweet, sour, salty, bitter, and umami. But what we perceive as flavor is far from simple. The tongue is covered in tiny clusters of sensory cells called taste buds, each tuned to these elemental categories. Yet, when combined with smell, temperature, texture, and even sound, your brain creates vast variations that feel infinite. A crunchy apple versus a soft one doesn't just differ by texture. The sound of the bite actually alters perceived freshness. The fizz of a carbonated drink heightens acidity, while warmth enhances sweetness. The brain merges these sensations seamlessly, sculpting each meal into an experience rather than a formula. What you call taste is really a symphony of senses, an ever-shifting conversation between your body and your imagination, turning molecules on the tongue into entire worlds of flavor in your mind. Humans might actually have a 6th taste for fats. For decades, scientists believed there were only 5 basic tastes. But recent research suggests we may have evolved another, a distinct sensitivity to fats. Specialized receptors on the tongue, tuned to certain fatty acids, trigger responses separate from sweetness or saltiness. This makes sense. Biologically, Fat is energy-rich, vital for survival, and deeply rewarding to the brain. The creamy smoothness of chocolate, the richness of butter, the comforting flavor of warm soup, all carry subtle signals that activate this hidden sense. Some people are more sensitive to these fatty notes than others, influencing appetite and food preference. Interestingly, those most attuned to fat's presence often eat less of it because their brains detect it sooner. Fat, once thought to be purely texture, is turning out to be a flavor of its own, the quiet, luxurious heartbeat of the culinary world. Cats can't taste sweetness at all. To a cat, sugar might as well be sand. Unlike humans, cats lack a key protein needed to detect sweet flavors. Their taste receptors for sweetness are broken, a genetic mutation that occurred long ago in their carnivorous ancestry. Since their diet consists almost entirely of meat, they never needed to recognize carbohydrates. While humans crave chocolate and fruit, cats feel nothing at all from sugar. Yet, they're not deprived. They have heightened senses for other tastes, especially amino acids found in flesh. Some even respond to savory compounds that humans barely notice. This peculiar blindness to sweetness shows how evolution tailors senses to survival. Every creature's perception of flavor is a reflection of what it needs most. For cats, sugar never mattered, but the scent of prey and the taste of protein define their entire sensory world. Fish can taste with their entire bodies. Many fish live in environments where sight and smell are unreliable, so they evolved a remarkable adaptation: taste buds scattered across their skin, fins, and even tails. A catfish, for example, can sense chemical traces in the water simply by swimming through them. Its entire body acts like a tasting instrument. These external taste buds detect amino acids, salts, and other molecules released by prey or plants. Some species have over 100,000 of them, turning their bodies into living maps of flavor and chemistry. Imagine being able to sense the faint sweetness of algae or the metallic tang of minerals without opening your mouth. For fish, taste isn't confined to eating. It's a form of environmental awareness, a way of exploring the liquid world they inhabit. In their quiet rivers and dark ocean depths, taste is how they see. Octopuses can taste with their arms. Each of an octopus's 8 arms is lined with hundreds of suckers, and each sucker is capable of independent taste and touch. When an octopus explores its surroundings, it doesn't just feel texture, it tastes it. These specialized cells can detect chemicals released by prey or hidden food sources, allowing the octopus to distinguish between rock, shell, and potential meal almost instantly. Its brain, distributed through its arms, processes this sensory information locally, granting each limb a degree of autonomy. This decentralized intelligence means an octopus can multitask in ways that seem almost alien, one arm investigating a shell while another prepares to strike. Their tactile taste sense turns the ocean floor into a map of flavor and signal. Every surface tells a story, and in that story, the octopus finds its next move, guided by a dance of touch and taste intertwined. Butterflies taste with their feet. When a butterfly lands on a leaf, it isn't just resting, it's tasting. Tiny chemoreceptors on its feet can detect sugars, toxins, and plant chemicals within seconds. This ability allows butterflies to test whether a leaf is suitable for laying eggs or feeding. A single tap of the foot reveals whether the plant will nourish their caterpillars or harm them. Female butterflies are especially discerning, performing delicate tasting dances before choosing the perfect site. Some can even sense pheromones or chemical cues from other species, avoiding competition. Imagine if, by stepping onto the ground, you could instantly know what it was made of and whether it would sustain life. For butterflies, this sensory power is survival. a delicate interplay between chemistry and instinct, guiding them through their fragile, floating lives among the flowers of the world. The sense of touch starts developing before birth. Long before sight or hearing awaken, the first sense to emerge in the womb is touch. By around 8 weeks of gestation, a developing baby begins responding to gentle contact, even before the brain is fully formed. As nerves and skin grow together, tactile signals help shape the brain's architecture, guiding connections that will one day control movement, perception, and emotion. Touch teaches the body where it begins and ends, defining the boundaries of self. Even after birth, this sense remains central to human growth. Gentle contact, a parent's hand, a soft blanket, a warm bath, releases hormones that calm the body and strengthen neural pathways. In this way, touch is the first language we ever speak, and perhaps the last we forget. It is the silent foundation of every other sense, the one that teaches us what it means to exist in a body. Your skin has more than 20 types of nerve endings. The human skin isn't just a protective shell, it's a living map of sensation. Beneath each square centimeter lie millions of nerve endings specialized for different signals: pressure, vibration, temperature, stretch, pain, and texture. Some respond to a feather's brush, others to deep pressure or heat. Certain receptors fire only when you're moving, others stay silent until the slightest change in temperature wakes them. Collectively, they form the body's largest sensory organ, constantly sending information to the brain about what touches you, how fast, and how strong. Even the tiniest shift, a grain of sand, a drop of water, a whisper of air, has its own neural signature. The richness of touch is what lets you distinguish silk from stone, warmth from cold, safety from danger. Through your skin, you are in constant conversation with the physical world, every moment alive with quiet messages. Some people can feel touch that others can't even detect. Not all skin is equal in its sensitivity. Some individuals have an extraordinarily fine sense of touch, able to feel textures and vibrations below the threshold of normal perception. These hypersensitive people can detect a single human hair brushing against the skin, or discern microscopic differences in surfaces by fingertip alone. In extreme cases, this sensitivity can border on painful clothing tags, or soft fabrics might feel unbearable. Scientists suspect genetic variations or differences in nerve density create this heightened awareness. Artists, surgeons, and musicians sometimes benefit from unusually refined tactile acuity, allowing greater control and precision. Yet for others, it's a constant challenge. The world itself feels too vivid. Touch, after all, isn't just mechanical, it's deeply emotional. What feels soft to one person might feel sharp to another. Our bodies don't just sense the world, they interpret it, each in their own way. There's a rare condition where touch and emotion are linked so strongly, it can be overwhelming. For most people, touch is comforting, grounding. But for those with mirror touch synesthesia, the experience becomes nearly unbearable. When they see someone else being touched, their own bodies echo the sensation, as if it's happening to them. Watching someone brush their arm can make them physically feel it. This overlap between empathy and sensation blurs the boundary between self and other. Scientists believe it results from unusually strong connections between the brain's somatosensory and mirror neuron systems, circuits that simulate what we see others experience. For some, it brings profound compassion and sensitivity for others. Sensory overload. It shows just how fluid perception can be, how our nervous systems are not isolated, but entangled. Touch isn't only physical, it's relational, emotional, and deeply human. Through it, we feel not just our own lives, but the echoes of those around us. You can feel heat and cold through entirely different receptors. Temperature is not a single sensation, but two, carried by distinct nerve fibers that respond separately to warmth and cold. The cold receptors activate when temperatures drop, while warm receptors fire as they rise. Yet these signals combine in your brain to create the unified feeling of temperature. When both fire together, you experience paradoxical sensations, like the tingling burn of menthol or chili. Some nerve endings even mistake chemical stimuli for temperature, which is why mint feels cool and cinnamon feels hot. This intricate system helps protect the body from extremes, prompting reflexes long before you consciously react. But it also gives temperature its emotional depth, the comfort of warmth, the sharp alertness of cold. Your skin doesn't just measure degrees, it translates energy into feeling, turning physics into the language of comfort, caution, and touch. The lips are one of the most sensitive parts of the human body. Packed with dense clusters of nerve endings and nearly devoid of protective layers, the lips are astonishingly responsive to touch, texture, and temperature. They contain around 100 times more nerve endings than the skin on your fingertips. This hypersensitivity allows subtle distinctions: the warmth of a cup, the softness of fabric, the closeness of another person. Because lips also lack sweat glands and hair, they feel temperature changes instantly. Their redness comes from blood vessels lying just beneath the surface, adding both warmth and sensitivity. Beyond biology, the lips are also tied to emotion. The same neural regions that process touch here are linked to pleasure and social bonding. A kiss, a sip, a whisper, each carries far more sensory information than you might imagine. The lips are not merely for speech or nourishment, but for connection, translating touch into intimacy. Blind people can read textures with incredible precision, far beyond sighted limits. When vision is lost, the brain doesn't go silent. It rewires itself. In people who are blind, the visual cortex, usually dedicated to sight, becomes active during touch-based tasks like reading Braille. This neural adaptation grants extraordinary sensitivity to texture and detail. Some blind individuals can distinguish patterns only a fraction of a millimeter apart, surpassing the tactile resolution of sighted people. Scientists have found that this happens because the brain reallocates unused visual circuits to enhance touch perception, sharpening the sense of texture and shape. The fingertips, already densely innervated, become even more responsive with practice. Touch becomes not just a substitute for sight, but a new kind of vision, one that perceives through contact rather than light. It's a reminder that the senses aren't fixed boundaries, but flexible tools, capable of profound transformation when one door closes and another opens. The feeling of being ticklish evolved as a form of social bonding and self-defense. Tickling is one of the strangest human sensations, both delightful and unbearable. Scientists believe it serves two intertwined purposes: play and protection. In social contexts, tickling encourages laughter and bonding, strengthening trust between parents and children, friends, or partners. Yet the same sensation also evolved as a defensive reflex. The most ticklish areas, ribs, neck, armpits, are also vulnerable to attack. The involuntary squirming and laughter that follow may have once trained the body to react quickly to unexpected contact. Interestingly, you can't effectively tickle yourself because your brain predicts your own movements and cancels the surprise. Ticklishness, then, lives in that narrow space between anticipation and unpredictability, a playful paradox at the heart of human touch. It reminds us that sensation is as much about emotion and relationship as it is about nerves and skin. Phantom limb sensations reveal how touch is mapped inside the brain. When someone loses a limb, they often continue to feel it. Warmth, itching, pressure, even pain, as if it's still there. These phantom limb sensations reveal that the experience of touch isn't confined to the body, but encoded in the brain's somatosensory map. Each body part corresponds to a region in the cortex, forming a detailed internal representation known as the homunculus. When a limb disappears, its brain region remains active, sometimes triggered by nearby areas. Touching the face of an amputee, for instance, might cause sensations in their missing hand. Mirror therapy, which uses visual feedback to trick the brain into seeing the limb again, can reduce phantom pain, showing how perception can be reshaped by illusion. In the end, touch isn't limited to where your skin begins and ends. It lives in the architecture of the mind itself. Your brain constantly predicts what you're about to feel before you actually feel it. Every touch, every movement, every texture you encounter passes through a predictive filter. Your brain doesn't wait for information to arrive, it forecasts it. Before your hand even reaches for an object, your sensory cortex anticipates the pressure, temperature, and weight you'll experience. This prediction helps you interact smoothly with the world, adjusting your grip before feedback arrives. When something unexpected happens, a surface is colder, heavier, or rougher than imagined, your brain rapidly updates its model of reality. This process, called predictive coding, saves immense processing power, allowing sensation to feel instantaneous. It's why self-tickling fails. The brain expects it, so the sensation feels muted. In essence, perception is less about receiving information and more about confirming expectations. Your senses aren't passive windows, they're active storytellers, constantly revising their tales as the world unfolds beneath your fingertips. We can feel sound vibrations through our skin. Sound isn't just something we hear, it's a physical vibration that moves through air, water, and even our bodies. Low-frequency waves, especially bass tones, can be felt as gentle tremors in the chest or fingertips. The skin contains mechanoreceptors sensitive enough to detect these subtle movements, converting acoustic energy into tactile experience. This cross-sensory overlap enhances how we perceive music. The deep resonance of a drum or the hum of an engine vibrates through us, adding texture to hearing. In experiments, people deprived of hearing can still detect rhythm and tempo through vibration alone. The body, in a sense, becomes an extension of the ear, an instrument tuned to the silent pulse of motion. Feeling sound reminds us that perception isn't confined to one sense at a time. It's a whole-body conversation with the physics of the world. Some deaf people use vibrations to experience music. For individuals who can't hear, music doesn't disappear, it transforms. Deaf musicians and listeners often use vibration as a way to feel rhythm, melody, and emotional nuance. They rest their hands on speakers, stand barefoot on wooden floors, or use wearable devices that translate sound frequencies into pulses against the skin. The brain, ever adaptable, learns to interpret these vibrations as patterns of meaning. Some deaf performers compose by visualizing frequencies, while others describe hearing with their bodies. The deep hum of bass in the chest, the sharp flicker of high notes on the fingertips. This tactile engagement with music reveals how fluid the boundaries of sense can be. Sound is vibration, and vibration is touch. The experience of art, then, isn't limited by the ear. It's something we can feel, live, and interpret through every fiber of the body. Your ears never truly stop hearing. Your brain just learns to tune sounds out. Even in deep sleep, your ears remain awake. They continue to receive sound, sending signals to the brain that are mostly ignored. The filtering happens not in the ear, but in the auditory cortex, where the brain decides what matters. Familiar, repetitive noises, the hum of a refrigerator, the ticking of a clock, fade into the background through a process called habituation. But an unusual sound, like a sudden creak or whisper, breaks through instantly. This selective attention evolved for survival, helping us rest without losing vigilance. Yet it also reveals how subjective hearing is. Silence is never truly silent, just a quieting of awareness. In the hush of night, your brain still listens, not to every sound, but to the patterns it deems important. The world continues to hum softly around you, even when you no longer notice. The quietest sound a human ear can detect moves the eardrum less than the width of an atom. At the threshold of hearing, sound becomes almost impossibly small. A whisper, a leaf rustling, a far-off breeze. These gentle waves move the eardrum by less than the diameter of a single hydrogen atom. Yet the ear's mechanical precision translates that minute vibration into a cascade of signals through tiny bones, fluid waves, and microscopic hair cells in the cochlea. Each cell resonates to a specific frequency, creating a map of sound across your auditory landscape. This sensitivity borders on the miraculous. The ear detects pressures 1 billion times weaker than those that would damage it. In quiet moments, your body stands on the edge of physics, capable of registering the faintest tremor in air. Hearing isn't just about volume, it's about attention to the smallest movements. Proof that even the gentlest whisper carries the power to be felt. Your brain can locate the source of a sound using differences smaller than a microsecond. Your ears work together like an exquisite detection system, able to pinpoint where a sound originates with almost impossible precision. When something makes a noise, the sound reaches one ear just a fraction of a moment before the other, a delay so small it can be less than 1/1,000,000th of a second. Yet your brain detects that difference, instantly calculating direction and distance. Even tiny variations in volume and phase help triangulate the exact position of a rustling leaf, a voice, or a footstep. The auditory cortex maps this data in real time, turning milliseconds into geometry. It's how you can close your eyes and still point unerringly toward a sound source. This ability evolved from survival, locating predators, prey, and the movements of others in darkness. Your head is small, but your timing is astonishing. A living sonar built into the silence between heartbeats. Some people experience earworms, songs that loop in the brain, as an auditory hallucination. A catchy melody that refuses to fade, the mysterious earworm. For most people, it's a harmless mental echo, but for some, these loops become vivid auditory hallucinations, complete with tone, rhythm, and texture. The phenomenon arises when parts of the brain's auditory cortex replay stored sound patterns without input from the ears. It's as though your brain's jukebox gets stuck on repeat. Stress, fatigue, and repetition can trigger the loop, but researchers think it serves a purpose, reinforcing memory through rehearsal. Musicians, in particular, experience earworms more intensely because their brains are wired for sound prediction. What's remarkable is that the sound doesn't really exist. Your brain is creating it from memory, using the same circuits that process actual hearing. Every hum, every chorus trapped in your mind is a ghost of sound, an invisible concert, performed by the imagination itself. Bats hear echoes up to hundreds of times faster than humans can. In the dark, bats see with sound. Their ultrasonic cries bounce off objects, returning as echoes that paint a vivid map of their surroundings. But what truly amazes scientists is their speed. A bat's brain processes these echoes up to hundreds of times faster than ours could. This rapid feedback lets them detect a flying insect in total darkness and adjust their flight path instantly. Some species emit over 100 clicks per second, forming a continuous stream of acoustic information. Their auditory systems are so sensitive they can detect differences in echo timing smaller than a microsecond, revealing not just location but shape, distance, and texture. To a bat, sound is not abstract, it's tangible. The air around them shimmers with invisible outlines of the world. Where we might see only darkness, bats experience a detailed flickering landscape built entirely of echoes. Elephants can hear sounds below the range of human hearing. Deep in the savannas, elephants communicate using rumbles so low-pitched that we can't hear them at all. These infrasonic calls vibrate through the ground and air, traveling vast distances, sometimes more than 6 miles. Elephants sense them not only through their enormous ears, but also through the sensitive pads on their feet, detecting minute seismic tremors. These low frequencies carry social information, warnings, greetings, and even emotional tones. Scientists have recorded family groups answering each other across open plains, long before they come into sight. It's as though the Earth itself becomes a shared telephone line. Humans can feel similar vibrations if amplified, but to elephants, they are as clear as speech. Their hearing reaches downward into frequencies we can only imagine, a secret communication woven through soil and sound, linking herds across invisible horizons of vibration. Whales communicate with infrasonic sound that travels thousands of miles. Beneath the ocean's surface, whales sing songs that can circle the world. Some of their calls reach frequencies so low that they travel through seawater for thousands of miles without fading. These infrasonic notes roll through the deep like invisible waves, connecting distant pods across entire oceans. Blue whales, for instance, can produce sounds below 20 Hz, vibrations more felt than heard. Scientists believe these immense voices help them navigate, find mates, and coordinate migrations across vast distances. Hydrophones placed deep underwater have recorded patterns so long and structured they resemble music, shifting subtly year by year. The ocean itself becomes a resonant chamber, carrying messages farther than any human technology could without distortion. For the whales, the sea is not silent. It's filled with a slow, haunting language that wraps around the planet in endless, liquid conversation. Owls can pinpoint prey in total darkness using hearing alone. An owl doesn't need light to hunt. Its face, shaped like a satellite dish, funnels sound toward its asymmetrically placed ears, one slightly higher than the other. This uneven design allows the owl to detect minute differences in timing and intensity between its ears, building a three-dimensional picture of sound. It can locate a mouse under a blanket of snow, guided purely by the faint rustle of movement. In experiments, owls with eyes covered still strike prey with near-perfect accuracy. Their brains contain specialized neurons that respond to both direction and elevation of sound, mapping space in exquisite detail. The silence of their flight, achieved by uniquely fringed feathers, ensures nothing interferes with that acoustic vision. For an owl, darkness is irrelevant. The night is full of sound shapes, living echoes of every heartbeat and whisper in the forest below. Your sense of balance lives in your inner ear. Hidden deep inside each ear is a labyrinth of fluid-filled chambers called the vestibular system, your internal compass. Tiny crystals and hair cells within these semicircular canals detect changes in movement, tilt, and acceleration. When you turn your head, the fluid shifts, bending delicate cilia that signal the brain about your body's orientation. Together with your eyes and muscles, this system keeps you upright, steady, and aware of which way is up. Even the smallest disturbance, fluid imbalance, infection, or motion can send confusing signals, producing dizziness or vertigo. Remarkably, your sense of balance works even in darkness, or with your eyes closed. It's entirely mechanical, relying on physics rather than vision. This hidden sense operates quietly, moment by moment, adjusting every step, every nod, every glance. Without it, the world would constantly tilt and spin beneath your feet. When you spin, fluid in your ears keeps moving. That's why you feel dizzy. After you twirl or turn quickly, the world seems to keep spinning, even when you stop. This sensation comes from the fluid inside your inner ears, semicircular canals, which detect rotation. As you move, the fluid lags slightly behind, bending sensory hairs that signal acceleration to your brain. When you stop, the fluid keeps swirling for a few seconds, fooling your brain into thinking you're still in motion. The conflicting messages, eyes seeing stillness, ears sensing movement, create that familiar dizzy disorientation. Children often chase this feeling playfully, laughing as their brains try to reconcile the contradiction. But in extreme cases, such as motion sickness, the mismatch between visual and vestibular signals becomes overwhelming. Dizziness is your body's way of saying, something doesn't add up. The sensation fades as equilibrium returns, proof that even balance has momentum, echoing long after motion ends. Astronauts' balance systems can become confused in zero gravity. On Earth, gravity constantly pulls on the fluid in your inner ear, giving your brain a stable sense of up and down. In space, that cue disappears. Astronauts' vestibular systems struggle to interpret motion without the familiar tug of gravity, causing space adaptation syndrome, essentially cosmic vertigo. The brain receives mixed signals. Eyes report movement, but the inner ear feels none. This mismatch can lead to disorientation, nausea, and a peculiar floating sensation that can last for days. Over time, the brain adapts, reinterpreting movement cues to function in microgravity. Interestingly, when astronauts return to Earth, the confusion reverses. Gravity feels unfamiliar again. Balance, it turns out, isn't absolute. It's a relationship between the body and its environment. In orbit, humans relearn what up means, proving that even something as fundamental as equilibrium is shaped by the pull of a planet. Some fish sense movement through a pressure-detecting lateral line. Along each side of a fish's body runs a row of tiny, fluid-filled canals called the lateral line system. Within them are hair cells similar to those in the human inner ear, sensitive to pressure changes and vibrations in the water. This hidden sense allows fish to detect movement, current, and even the presence of nearby creatures without seeing them. In a dark river or murky lake, a fish can feel an approaching predator through the faint ripples it makes. Schooling fish use their lateral lines to coordinate, turning in near-perfect unison without collision. It's a sixth sense of flow and proximity, tuned to the fluid world they inhabit. For creatures that live immersed in motion, this sensitivity is everything. A map of invisible waves, a perception of presence through pressure alone. To a fish, the water is alive with touch. Your eyes detect only a tiny sliver of the electromagnetic spectrum. The light you see, reds, blues, greens, and all the colors between, is only a narrow band of electromagnetic radiation. Beyond it stretch wavelengths both shorter and longer: ultraviolet, infrared, X-rays, radio waves, microwaves, gamma rays. Your retinas, equipped with just 3 types of color-sensitive cones, translate this limited range into the visible world. Yet this sliver feels infinite, painted into sunsets, oceans, and stars. Bees see ultraviolet, snakes perceive infrared, and some fish detect polarization, realms invisible to us. The universe around you teems with hidden light, humming with colors beyond imagination. What you call seeing is really sampling, your brain interpreting one octave of a cosmic symphony. It's humbling to remember that the rainbow is only a fragment of reality, a small, bright window through which your eyes glimpse the vast, invisible spectrum of existence. Bees see ultraviolet patterns invisible to humans. To human eyes, a flower is simply colorful to a bee. It's a luminous landing strip. Many flowers bear ultraviolet markings, patterns invisible to us, but blazing bright in the bee's vision. These nectar guides point directly toward the center, leading pollinators to their reward. Bees possess 3 types of photoreceptors like us, but one is tuned to ultraviolet instead of red. This shift opens an entirely different color world where petals shimmer with secret contrasts and glowing edges. The patterns aren't decorative. They're maps designed by evolution for mutual benefit. Without bees' ultraviolet sight, pollination might falter without the flower's patterns. Bees would wander blind. Together, they form one of nature's most elegant collaborations, a dialogue written in light we can't see. To the bee, the garden is a gallery of luminous signals, invisible symphonies painted on every petal. Snakes can see heat with infrared-sensitive pits. Pit vipers, pythons, and boas possess a remarkable adaptation, tiny heat-sensing organs near their nostrils called pit organs. These structures detect infrared radiation, the warmth emitted by living bodies, allowing snakes to form thermal images of their surroundings, even in complete darkness. Each pit contains a thin membrane rich with nerve endings that respond to minute temperature differences, as small as a fraction of a degree. The data merges with visual input, giving the snake a composite sense of sight and heat. To them, a mouse glows like a small star in the night. This thermal vision helps them strike with perfect accuracy, guided by warmth rather than light. Where we see darkness, snakes perceive a glowing landscape of heat signatures, a world illuminated not by photons, but by the gentle radiation of life itself. Mantis shrimp have up to 16 types of color receptors. We have only 3. Human eyes rely on 3 cone types to perceive millions of colors, but mantis shrimp take that to an otherworldly extreme. Their compound eyes contain up to 16 different photoreceptor types, tuned to ultraviolet, visible, and polarized light. Each eye moves independently, scanning the ocean with extraordinary detail. Yet, paradoxically, mantis shrimp may not see color as vividly as we do. Instead, their brains process information more like a scanner than a painter, rapidly detecting differences rather than blending hues. Their vision is perfectly adapted for life on coral reefs, where polarized reflections reveal prey and predators hidden from others. The world through their eyes might appear as a mosaic of shifting signals, dazzling yet functional. To them, the sea is an electric tapestry of light, unseen by any other creature, a living kaleidoscope of physics and perception intertwined. Birds see colors that don't even exist in human experience. Most birds are tetrachromats. They possess 4 types of color receptors, adding ultraviolet sensitivity to the standard trio humans use. This extra cone opens an entire dimension of color beyond our imagination. They don't just see more vivid shades, they perceive combinations we can't even conceive. Ultraviolet mixed with blue or yellow, creating colors with no human equivalent. Feathers that look plain to us may blaze with iridescent patterns in a bird's eyes, signals of health, species, or attraction. Some flowers and fruits evolved specifically to stand out in this ultraviolet world. For birds, the sky is layered with hues we'll never name, and sunlight sparkles with hidden gradients. Their vision reminds us that reality isn't limited by physics, but by perception. and that the beauty we see is only one small slice of what truly shines around us. Some deep-sea creatures create their own light just to see. In the abyssal depths, where sunlight never reaches, life invents its own illumination. Many deep-sea species use bioluminescence, chemical reactions that emit light, not only to lure prey or signal mates, but also to see. Certain fish produce glowing bacteria that coat their skin or fill specialized organs, casting soft blue-green halos into the dark. Others flash bursts of light to outline nearby shapes, like brief lightning in the deep. Some squid use counter-illumination, glowing downward to erase their shadows from predators below. To these creatures, light isn't a constant gift from the sun, it's a resource they must generate. Every flicker becomes a moment of vision, a self-made sunrise in eternal night. In that black water, seeing and shining are the same thing, perception born from within, where darkness becomes its own kind of brilliance. Your brain fills in blind spots in your vision every second. Each of your eyes has a small region where the optic nerve exits the retina, a patch with no light-detecting cells at all. This is your blind spot. Yet you never notice it, because your brain quietly edits it out. Using information from the other eye, along with pattern recognition and prediction, your visual cortex paints in the missing detail automatically. If you close one eye, the world still appears seamless. Your brain invents what should be there. This silent correction happens continuously, a living Photoshop that stitches reality together. In experiments, objects placed precisely in the blind spot simply vanish. What you see is not raw data, but an elaborate reconstruction, an illusion so convincing you never realize it's incomplete. Your mind is not a camera, it's an artist, always filling the void with its best guess of the truth. You actually see everything upside down, your brain flips it automatically. When light enters your eyes, it passes through the curved lens and projects an inverted image onto your retina. The top of the world lands at the bottom, and left becomes right. Yet your brain corrects this without effort, turning the image upright before you're aware of it. If you wear inversion goggles that flip vision again, your mind eventually adapts. Within days, it relearns up and down. This automatic correction reveals that sight is not just mechanical, but interpretive. You don't truly see the world as it is, you see your brain's version of it, stabilized, oriented, and filtered for meaning. The inversion of vision reminds us that perception is flexible, that even gravity and direction are subjective in the realm of the mind. Every glance you take is, in essence, a quiet miracle of reinterpretation. Your eyes constantly move even when you think you're staring still. Try to hold your gaze perfectly steady, you can't. Your eyes are never motionless. Even when fixated on a single point, they perform tiny, jittering movements called microsaccades. These constant shifts prevent the photoreceptors in your retina from becoming desensitized to unchanging light. If your eyes could truly freeze, your vision would fade into gray within seconds. These micro-movements refresh your view, keeping edges sharp and details alive. They also help your brain detect contrast, motion, and depth. You see stability, not because your eyes are still, but because they never stop moving, a paradox of perception. Behind every glance lies a hidden dance, millions of micro-adjustments choreographed to keep the world vivid. Vision, it seems, depends on restlessness. Your eyes, even in calm, are always in motion, quiet seekers of light, trembling softly beneath the surface of stillness. Peripheral vision is terrible at color, but amazing at motion detection. Look straight ahead, and your central vision captures vivid detail, rich colors, sharp lines, and fine textures. But at the edges, things blur and fade. The retina's periphery is dominated by rod cells, which are highly sensitive to light and movement, but nearly colorblind. This trade-off evolved for survival. Motion at the edge of vision could signal danger. A flicker in the corner of your eye instantly draws attention, activating your reflexes long before conscious thought. In dim light, rods outperform color-sensitive cones entirely, explaining why twilight scenes seem washed in gray. Artists and filmmakers use this quirk to create tension or realism. What's unseen but moving feels alive. Peripheral vision is your silent guardian, scanning the margins of awareness. It sacrifices color for vigilance, reminding us that even in stillness, your eyes are always watching the horizon for change. Your pupils expand when you look at something you love. The eyes reveal emotion long before words can. When you look at something, or someone, that stirs you, your pupils instinctively widen. This dilation isn't under conscious control, it's driven by the autonomic nervous system, responding to arousal, fascination, or affection. Artists of the Renaissance, without knowing the biology, often painted their subjects with slightly enlarged pupils to make them appear more alive, more beautiful, more human. Studies show that our brains register dilated pupils in others as a subtle cue of attraction and warmth. The same reflex also occurs in wonder when you gaze at starlight, color, art, or even new knowledge. Your eyes literally open wider to the world. Pupils expand to let in more light, but they also reflect an inner brightness, a biological echo of attention itself, revealing how deeply seeing and feeling are intertwined. After staring at one color, your brain invents its opposite. Fix your gaze on a red square for a while, then shift your eyes to a white surface. You'll see a ghostly green shape appear. This illusion is called an afterimage, and it happens because your cone cells, responsible for color vision, become fatigued from overstimulation. When they rest, their opposing color receptors, in this case green, fire more strongly, creating a phantom hue. The same happens with blue and yellow, black and white. Your brain's color system is built on contrast, not absolute tones, interpreting light in pairs. This is why complementary colors feel so vibrant together. They excite opposite sides of your visual circuitry. The afterimage reminds us that vision is not fixed, it's dynamic and self-correcting, forever recalibrating balance. What you see after light disappears isn't a trick. It's your brain's lingering memory of contrast, painting the world from within. Light doesn't have color. Your brain creates it. Color doesn't exist in the outside world. It's not a property of light itself, but a perception created by your brain interpreting wavelengths. Sunlight contains every color at once, pure energy, invisible until it strikes matter and reflects differently from each surface. Your eyes convert these wavelengths into electrical signals, and your brain translates them into sensations of red, blue, or green. A strawberry isn't red, it reflects light at a wavelength your mind interprets that way. In darkness, those wavelengths vanish, and so does color. What you experience as the vivid palette of reality is an internal code, a projection built inside your mind. Physicists describe light as vibration, and energy artists describe it as emotion. In truth, it's both. Color is the meeting point between physics and perception, a silent agreement between the outer world and the one within. Some people have an extra cone type and can see millions more colors. Most humans are trichromats, with 3 cone types tuned to red, green, and blue. But a rare few, perhaps 1 in every 200 women, have a 4th cone, extending their color range into shades the rest of us can't even imagine. This condition, called tetrachromacy, grants perception of up to 100 million distinct hues. A wall painted beige might reveal hidden undertones of pink or gold. A sunset might shimmer with invisible gradations. Interestingly, tetrachromats don't always realize their difference. To them, the world simply looks normal. It's the rest of us who seem colorblind. Their eyes capture more information, but the brain still decides what to emphasize. This discovery reveals how subjective vision truly is. Reality filtered through biology. Somewhere out there, someone sees subtleties in the sky that you and I can't even name. The world looks dimmer to men than to women on average. Studies have found that men and women often perceive light and color slightly differently. On average, men's eyes require marginally more brightness to see the same shade as vividly. This may arise from differences in the X chromosome, which carries many genes related to color-sensitive cones. Women, having two X chromosomes, sometimes benefit from enhanced color discrimination, especially in the red-orange range. Men, conversely, are more prone to mild color blindness, particularly in greens and reds. These distinctions are subtle, often unnoticed in daily life, yet they remind us that perception is deeply personal. Even among humans, the same sunset might not look identical to everyone standing beneath it. The world outside is constant. The light within each eye is what varies. We don't just share one reality, we each see a slightly different one, shaped quietly by biology. Goldfish can see infrared light. The humble goldfish perceives a world hidden from human sight. Its eyes can detect both ultraviolet and infrared wavelengths, stretching beyond the visible spectrum at either end. Infrared sensitivity allows goldfish to sense the faint warmth of sunlight filtering through murky water, helping them navigate and detect predators. Ultraviolet perception, meanwhile, sharpens contrast and reveals reflections invisible to us. This broad spectral range makes goldfish vision remarkably adaptive, suited to shifting water clarity and depth. For humans, infrared and ultraviolet are mere concepts. We build cameras to see what our eyes can't. But for a goldfish, it's ordinary reality. Every glimmer of light holds extra information. Every ripple carries hidden hues. The pond that looks brown and still to us shimmers with color and heat to them. A reminder that even in familiar places, whole dimensions of sight can remain unseen. Some frogs use light-sensitive molecules on their skin to detect day and night. Long before they could see with eyes, ancient amphibians may have sensed light through their skin, and some modern frogs still do. Embedded in their skin are photoreceptive molecules similar to those in eyes, tuned to brightness rather than image. These dermal photoreceptors allow frogs to detect changes in daylight and shadow even when buried in mud or resting underwater. It helps regulate their internal clocks, guiding when to hunt, hide, or sing. In some species, the pineal gland on top of the head also acts as a third eye, sensing light intensity. This distributed form of vision isn't about seeing pictures. It's about feeling the rhythm of the sun and moon. Through their skin, frogs live in tune with the cycles of light that shape their wetlands, their songs rising and falling with the slow pulse of the Earth's illumination. Certain shrimp punch so fast they create flashes of light. The mantis shrimp, already famous for its extraordinary vision, is also one of the ocean's most powerful strikers. Its raptorial claw can accelerate faster than a bullet, reaching speeds so extreme that it creates a cavitation bubble, a pocket of vacuum that collapses with explosive force. When the bubble implodes, it releases light, heat, and sound in a burst of energy called sonoluminescence. The temperature inside that momentary flash can rival the surface of the sun. The shrimp, in effect, produces light through impact alone. To its prey, the strike is instantaneous, death by pressure wave. To physics, it's a miniature star born underwater. Few animals blend such violence and beauty so perfectly, a creature that both sees and creates light in ways beyond human comprehension. In the darkness of the reef, the mantis shrimp is both predator and tiny cosmic event. The sense of time is a sense too, and it can stretch or shrink. Time feels constant, but your brain perceives it like any other sense, relative, elastic, and deeply subjective. In danger or excitement, neural processing speeds up, making moments seem to unfold in slow motion. In calm routine, the opposite happens. Time slips past unnoticed. The brain's internal clock relies on networks that measure change, not seconds, comparing the pace of sensory input to memory. That's why novelty makes time feel longer. New experiences fill perception with fresh data, while repetition leaves fewer mental traces. Even temperature, emotion, and heartbeat can alter time's rhythm. In deep meditation or fatigue, the minutes dissolve entirely. Time isn't something outside you, it's something your brain continually constructs, as fluid and adaptable as color or sound. Every moment you live is a sensory illusion of duration, a personal tide moving through awareness itself. Fear can make time seem to slow down. In moments of intense fear, a fall, an accident, a near miss, many people report that time stretches. Each instant feels suspended, elongated, almost dreamlike. Scientists once thought the brain sped up like a high-speed camera, but experiments suggest a subtler truth. Emotion alters memory, not perception. During stress, the amygdala floods the body with adrenaline and attention, recording details more densely than usual. When recalled, those rich memories feel as if they took longer to occur. The sensation of slow time is the mind's way of acknowledging how much it absorbed in a heartbeat. This elastic sense of duration helped our ancestors survive danger, giving them a chance to react, decide, and remember. It reminds us that time isn't uniform. It bends around emotion, stretching and compressing to match the pulse of the heart that measures it. Your brain can predict events before you consciously notice them. Every moment you experience is slightly delayed, the result of processing time. But your brain compensates by predicting what will happen next, allowing perception to feel instantaneous. This predictive mechanism operates so efficiently that you often respond before awareness catches up. In experiments, neurons fire milliseconds ahead of expected sensory input, essentially forecasting the future. It's how you catch a ball, play music, or finish someone's sentence. The brain continuously models the world, guessing outcomes and correcting errors in real time. When those predictions fail, as in illusions or surprises, you feel the world glitch. This constant forecasting saves energy and creates stability in a chaotic environment. Your senses don't merely receive reality, they anticipate it. Every sound, motion, and moment you perceive arrives through a veil of expectation, the brain's quiet attempt to live half a second ahead of time. You perceive the present slightly in the past, delayed by your brain's processing. What you think of as now already happened about a fraction of a second ago. It takes time for your senses to gather data, convert it into neural signals, and deliver it to consciousness. Light reaches your eyes almost instantly, but the brain's interpretation lags behind, syncing vision, sound, and touch into a coherent scene. To avoid confusion, your mind smooths the delay into a seamless present, stitching the past into what feels like the immediate moment. This temporal illusion keeps you coordinated and calm. Without it, the world would stutter like a broken film reel. You are, in a sense, always living slightly in memory, a fraction behind the true present. Yet because everyone shares this delay, we move through time together, unaware that each instant we call now is really a beautiful echo of what just was. Jet lag affects your body's internal sense of time, not just sleep. Your body is ruled by a master clock, a cluster of neurons in the brain called the suprachiasmatic nucleus. It synchronizes with light and dark, regulating temperature, metabolism, and hormone release. When you cross time zones, this rhythm falls out of sync with local daylight, creating jet lag. It's not simply tiredness, it's internal dissonance. Your organs still think it's midnight when morning arrives. Even digestion, alertness, and coordination follow the wrong schedule until the clock resets. Light is the strongest cue for recalibration. Exposure at the right moments gradually shifts the cycle back. Some animals, like migratory birds, adjust more easily, their circadian systems remarkably flexible. Humans eventually adapt too, but for several days, your body drifts between times, half in the old world, half in the new, a reminder that even time, inside us, needs light to find its rhythm. Your sense of direction is partly magnetic. Though subtle, humans may possess a faint magnetic sense. In controlled experiments, people sitting in darkness unconsciously reacted to changes in Earth's magnetic field. Their brain waves shifted as the field rotated, even though they couldn't consciously detect it. This suggests that within us lie magnetite crystals, tiny iron-based particles sensitive to geomagnetic forces, similar to those found in migratory birds and sea turtles. While our navigation relies mainly on vision and memory, traces of this ancient compass may still influence spatial orientation. Some people experience uncanny gut feelings about direction that prove accurate. If confirmed, it would mean humans share an ancestral sense stretching back to the earliest life forms that oriented toward magnetic poles. Perhaps deep in our cells, a silent compass still turns, an echo of evolution, pointing not north or south, but home. Birds and some humans have molecules that may detect Earth's magnetic field. Inside the eyes of migratory birds, and possibly humans, lies a light-sensitive molecule called cryptochrome. When struck by blue light, it forms paired electrons whose spins are influenced by Earth's magnetic field. The result is a visual pattern overlaying their sight, like a faint compass drawn across the world. Birds may literally see direction, sensing north and south as gradients of light intensity. Some research suggests humans also possess cryptochrome in their retinas, though ours seems dormant or weak. If activated, we might once have shared that sixth sense of orientation, a way to navigate without maps or stars. Even now, our biology remembers, magnetism passes through us, invisible yet constant. For creatures that migrate across continents, this molecular compass is a quiet miracle, guiding flight paths that trace invisible lines written into the very fabric of the Earth. Salmon navigate home using the planet's magnetic map. After years in the open ocean, salmon find their way back to the exact river where they were born, sometimes across thousands of miles. They do this using a built-in compass that reads Earth's magnetic field like coordinates. Each river's mouth has a slightly different magnetic signature, and salmon imprint it early in life. When they mature, they navigate by those cues, adjusting their routes as if following a map drawn in invisible lines. Scientists confirmed this by observing young fish raised in magnetic fields mimicking distant locations. They oriented themselves toward the corresponding direction of their home stream. It's an ancient form of navigation, older than roads or stars, powered by quantum-level sensitivity to the planet's magnetic field. In the silent depths of the ocean, where light cannot guide them, salmon feel their way home along the magnetic pulse of the Earth itself. Pigeons can sense subtle changes in air pressure as they fly. Pigeons are masters of orientation. able to find their way across unfamiliar terrain even when disoriented. Part of their secret lies in barometric sensitivity, an ability to detect minute shifts in atmospheric pressure. As they fly, specialized receptors in their middle ears sense changes in altitude and weather, allowing them to gauge position and distance. Combined with magnetic and visual cues, this creates a multisensory map of the world. Pigeons may even store pressure landmarks, recognizing familiar air patterns tied to specific locations. When storms approach, their sensitivity warns them long before the sky darkens. This hidden sense connects them directly to the living air, letting them read the invisible texture of the atmosphere. What looks like instinct is really an elegant fusion of physics and perception, a body tuned to the whisper of the wind itself. Sharks sense electric fields through pores on their snouts. Every living thing gives off a faint electric signal, generated by the movement of ions in cells. Sharks can detect these invisible fields through specialized pores called ampullae of Lorenzini, clustered around their snouts. Each pore opens to a gel-filled canal that transmits electrical information to sensory cells. This allows sharks to sense prey hidden under sand or navigate using Earth's magnetic field, which induces weak electric currents in seawater. Their sensitivity is astonishing. They can detect voltages as low as 1/1000th of a volt. To a shark, the ocean is alive with invisible lightning, a network of subtle pulses and currents. Vision and smell help them locate prey, but electricity gives them precision. In a way, sharks live in two worlds at once: the visible sea we know, and an unseen ocean of energy shimmering beneath every movement of life. Platypus is hunked by detecting electric signals from their prey. The platypus, with its duck-like bill and mammalian quirks, hides one of nature's most remarkable senses. Beneath the soft surface of its bill lie thousands of electroreceptors, capable of detecting the tiny electrical impulses produced by the muscles of worms, crustaceans, and insects. As it forages in muddy riverbeds, the platypus closes its eyes, ears, and nostrils, relying entirely on this electric sense to guide it. The combination of mechanoreceptors and electroreceptors creates a three-dimensional map of underwater prey. This makes the platypus one of the few mammals, alongside dolphins, to possess electroreception. What seems like a clumsy creature is, in fact, an exquisite hunter, reading the faint hum of life in the dark. For the platypus, sight and sound are optional. The world speaks in pulses and currents, a secret language of electricity woven through the water. Some fish communicate through electric pulses. In the black rivers of the Amazon, certain fish speak in flashes of electricity. Species like the electric fish and elephant nosfish generate weak electric fields that ripple outward, interacting with nearby objects and other fish. By modulating these signals, altering frequency, rhythm, and intensity, they send messages of identity, territory, and courtship. To them, the dark water is alive with silent conversation. Each species has its own dialect of pulses, and individuals recognize one another by their unique electric signatures. Some even adjust their signals to avoid interference, creating a constantly shifting chorus of invisible communication. Humans needed centuries to invent radio. These fish evolved their own long ago. Electricity for them isn't just power, it's language. Their world glows not with light, but with rhythm, a quiet electric hum that connects every living thing in the current. Plants can sense touch and change how they grow in response. Though they lack nerves or muscles, plants are exquisitely sensitive to touch. When a vine brushes against a nearby branch, it begins to curl and climb. When a leaf is stroked or shaken by the wind, microscopic changes ripple through its cells. This phenomenon, called thigmomorphogenesis, allows plants to adapt their shape to the world around them. Some grow thicker stems when regularly touched, strengthening against stress. Others redirect growth towards stability or light. Even brief contact can alter gene expression within minutes. The sensitive hairs of a Venus flytrap can detect a single brush from an insect, triggering one of nature's most elegant reflexes. Plants, it seems, don't just passively grow, they feel their environment in slow motion. Every breeze, raindrop, and grazing animal leaves an imprint. In their own quiet way, they reach toward the world not blindly, but responsively, attuned to every touch of life. Trees seem to hear sound vibrations from insects. It might sound poetic, but evidence suggests it's literally true. When scientists played recordings of caterpillars chewing leaves to certain trees, the plants increased chemical defenses, even though no real insects were present. Vibrations alone were enough to trigger a response. Trees can detect the unique frequencies of threats like chewing or buzzing, and prepare for attack by releasing bitter compounds or signaling nearby plants through airborne chemicals. They also seem to distinguish harmless sounds, such as wind, from those that matter. This sensitivity to vibration acts as an early warning system, invisible but effective. The forest, then, is far from silent. It hums with the language of pressure waves and motion. Each rustle, buzz, and footstep may be felt, not heard, by the trees themselves. The next time wind moves through a forest, imagine the trees listening, quietly, constantly, and deeply aware. Bacteria can sense light even without eyes. Single-cell bacteria, long before eyes evolved, could already detect light. They do this through photoreceptive proteins that change shape when exposed to photons, guiding movement toward or away from brightness. Some cyanobacteria can even focus light through their round bodies, acting like microscopic lenses, a primitive precursor to vision. This ability lets them navigate, photosynthesize, and avoid harmful radiation. In a sense, bacteria experience the world as gradients of energy, feeling light as warmth or guidance. These early photoreceptors were the ancestors of every eye that would follow, from the compound eyes of insects to the lenses of mammals. Long before creatures could see, life was already sensing brightness and shadow, tracing the boundaries between day and night. In their tiny way, bacteria were the universe's first witnesses of light, drifting specks that learned to follow the glow of the sun. Your gut contains sensors that can taste what you eat. Taste doesn't end at the tongue. Deep in your intestines, specialized cells known as enteroendocrine cells act as hidden taste receptors. They detect sugars, fats, and amino acids as food passes through, triggering hormonal responses that control digestion and appetite. These gut sensors even use some of the same molecular receptors found on your tongue, meaning your body tastes nutrients twice, once consciously in the mouth, and again silently in the gut. When these cells detect sweetness, they may prompt insulin release when they sense bitterness. They can slow digestion to protect against toxins. This inner tasting network helps balance energy, craving, and nutrition without your awareness. Scientists now believe these gut-based senses communicate directly with the brain through the vagus nerve, forming what some call the second brain. In essence, your body knows what it's eating before you do, a quiet intelligence working beneath thought itself. The heart has its own mini nervous system that feels in real time. Your heart is not merely a pump. It's a sensitive organ with its own network of neurons, about 40,000 of them, capable of processing information independently of the brain. This heart-brain monitors pressure, chemistry, and rhythm, adjusting each beat in response to emotion and environment. When you feel nervous, It quickens before you think. When calm, it slows as if exhaling. Signals from the heart travel upward to influence mood, decision-making, and even memory. Researchers have found that synchronized heart rhythms can foster emotional stability and coherence. Some traditions have long described intuition as something felt in the heart, and neuroscience now hints there's truth to that metaphor. The heart listens as much as it beats, responding moment by moment to the currents of feeling and physiology that pass through it. It doesn't think in words, it feels in rhythm. You can smell emotions. Fear, happiness, and sadness have distinct odors. Human sweat carries invisible chemical signatures that mirror emotion. In controlled studies, volunteers exposed to the scent of fear-based sweat showed heightened alertness, while those who inhaled happy sweat unconsciously smiled more. These emotional odors contain compounds like adrenaline byproducts or stress hormones that subtly communicate state of mind. Though we no longer rely on scent for survival as animals do, our bodies still broadcast these messages, whispers of emotion that others can detect without awareness. The nose bypasses rational thought, sending signals directly to the brain's emotional centers. This ancient communication once helped groups sense danger before seeing it. Even now, a room can feel tense or warm, partly because of invisible chemistry. We read each other not just with words or expressions, but through scent, the body's oldest, quietest language of empathy and instinct. Dogs can detect diseases through smell long before symptoms appear. A dog's nose is a marvel of biology, up to 100,000 times more sensitive than a human's. With over 300 million olfactory receptors, dogs can detect trace molecules emitted by the body's chemistry, even in concentrations as faint as 1 part per trillion. This super sense allows them to identify the unique odor signatures of diseases like cancer, diabetes, and viral infections before traditional tests can. Some trained dogs have accurately detected tumors hidden deep within the body or changes in blood sugar by smell alone. What they sense are metabolic byproducts, subtle shifts in chemistry that accompany illness. It's as if they can smell molecular imbalance itself. For them, the world is a tapestry of scent layered with meaning, emotion, health, time, identity. While we live by sight, dogs move through an invisible forest of fragrance, where even sickness has its own aroma. Bees can be trained to detect explosives by scent. With their extraordinary sense of smell, honeybees can identify chemical traces invisible to instruments. Scientists discovered that bees can be conditioned, much like dogs, to associate specific odors with a reward. By pairing explosive vapors with a drop of sugar water, bees learn to extend their proboscis whenever they encounter the target scent. In tests, they have detected explosives at concentrations as low as a few parts per trillion. Compact detectors even use tiny chambers filled with trained bees, where sensors monitor their reactions to air samples. Unlike machines, bees require no calibration, just light, warmth, and sweetness. Their ability arises from evolution. In nature, scent guides them to flowers and nectar miles away. Humanity simply borrowed that gift, transforming the pollinators' delicate noses into tools for safety. Even in science and security, the bee's quiet sensory genius continues to serve. Your sense of smell weakens as you age, especially for certain odors. Over time, the olfactory neurons responsible for detecting scent become less numerous and less responsive. This gradual decline, known as presbyosmia, affects nearly everyone past middle age. Certain odors, particularly sweet or floral ones, fade first, while sharper smells like smoke or vinegar linger longer. The loss isn't just sensory. It can affect appetite, memory, and emotional connection. since smell is deeply tied to pleasure and recall. Yet the brain adapts, amplifying attention to familiar scents and filling gaps with memory. Interestingly, some research shows that consistent exposure to varied odors may slow the decline, much like exercise preserves muscle. Smell training, deliberately inhaling different aromas daily, can even restore some sensitivity. Though aging dims the world's fragrance, it also deepens nostalgia. A single remembered scent can summon decades, bridging the space between fading senses and undimmed emotion. Some people can smell rain before it arrives. That unmistakable earthy fragrance drifting through the air before a storm is called petrichor. It forms when rain hits dry soil, releasing plant oils and a molecule named geosmin, produced by bacteria in the ground. Some humans can detect geosmin at astonishingly low concentrations, a few parts per trillion. When humidity rises or the first drops fall, these airborne molecules reach the nose, signaling that rain is near even before it begins. Evolution may have favored this sensitivity. Early humans who sensed coming rain could prepare for shelter or travel. To many, the scent evokes comfort and renewal, the world cleansing itself. The smell of rain isn't just chemistry, it's memory, longing, and the quiet recognition of change. When you inhale that earthy sweetness, you're sensing a dialogue between water, soil, and life itself, the planet breathing before the storm arrives. Humans might unconsciously choose partners based on smell compatibility. Studies suggest that scent plays a surprising role in attraction. Beneath conscious awareness, humans seem drawn to the natural body odors of those with dissimilar immune system genes, particularly in a group called the MHC complex. This genetic difference strengthens potential offspring by broadening immune defenses. In experiments where participants smelled warm t-shirts, they consistently preferred the scent of genetically compatible partners. Perfumes and soaps may mask it, but body odor carries silent biological messages of fertility and health. What smells appealing to one person may seem neutral or unpleasant to another. It's chemistry, not coincidence. Even in a crowded room, your subconscious may guide you towards someone whose scent feels inexplicably right. Beneath the surface of love and logic, your nose whispers a quiet truth. Compatibility can sometimes be sensed before it's ever seen. Your body odor is as unique as your DNA. Every person emits a distinctive scent signature shaped by genetics, diet, hormones, and even the bacteria living on their skin. Identical twins smell more alike than strangers, but never exactly the same. This individuality arises from the major histocompatibility complex, the same gene group that influences immune function and, subtly, attraction. Dogs and other animals use these cues to identify individuals, but humans perceive them subconsciously. Our personal scent is so consistent that researchers have identified people from their odor profiles with high accuracy. Even emotions like stress or happiness can temporarily alter it. You leave behind an invisible chemical fingerprint everywhere you go, in the air, on fabrics, on the skin of those you touch. Your scent tells your story without words, a molecular autobiography carried by every breath and breeze that moves past you. The new book, or old paper smell, comes from slowly decaying molecules. The scent of aging books, that warm, nostalgic aroma of libraries, is chemistry in slow motion. Paper and ink contain compounds like lignin and cellulose that, over decades, break down into aromatic molecules such as vanillin and benzaldehyde. These same compounds are found in vanilla and almond oils, giving old books their sweet, comforting fragrance. The new book smell, by contrast, arises from modern printing inks, glues, and coatings, releasing volatile organic compounds that fade over time. Together, these scents tell the story of materials aging, the quiet oxidation of wood, plant fiber, and time itself. To those who love reading, that fragrance becomes inseparable from memory and imagination, a sensory bookmark connecting past and present. Every library, in a way, breathes, a blend of history and chemistry rising softly from the pages of human thought. Space has a distinct smell, like seared metal and burnt steak. Astronauts returning from spacewalks often report the same thing, a lingering aroma on their suits and equipment. It's described as metallic, smoky, and slightly sweet, reminiscent of hot metal or charred meat. The scent doesn't exist in the vacuum of space itself, but forms when high-energy particles interact with spacecraft materials, creating reactive molecules that cling to surfaces. When astronauts re-enter the airlock, these compounds oxidize, releasing the smell of space. It's the scent of atomic reactions, ozone, and irradiated dust, the residue of cosmic energy. Some say it smells like adventure, others, like welding fumes or fireworks. In a sense, it's the aroma of starlight meeting matter, the universe leaving its fingerprint on everything that dares to cross into its emptiness. Even in silence, space has a scent, the burnt whisper of creation itself. Some people see colors when they hear music, a form of synesthesia. For individuals with chromesthesia, the senses intertwine in extraordinary ways. Sounds, especially music, trigger vivid bursts of color in their minds. A trumpet might flash gold, a cello deep blue, a voice soft rose or silver. These colors appear involuntarily, as real to them as the notes themselves. Each person's associations are unique. For one, middle C may always glow green, while for another, it radiates crimson. Brain imaging shows that auditory and visual regions activate simultaneously, blending perception into one multisensory experience. Many artists and composers throughout history, from Scriabin to Pharrell Williams, have described this gift. Synesthesia reveals how flexible the human mind truly is. Not a collection of separate senses, but a living network of intertwined impressions. When sound becomes color, perception transcends boundaries. A quiet reminder that reality is always richer than we know. Others can feel textures when hearing certain sounds. Some synesthetes don't see color in sound, they feel it. A piano note might produce the sensation of silk brushing the skin, while a trumpet blare feels rough, metallic, or sharp. This rare form, known as auditory tactile synesthesia, links hearing directly with touch. The brain's sensory regions overlap, so vibrations of sound stimulate tactile circuits. For those who experience it, the world is alive with texture. Voices have grain, wind chimes feel smooth, rain on a window ripples across the skin like fabric. The phenomenon shows that perception isn't divided into strict channels. It's a continuous field where one sense can spill into another. In a way, we all share echoes of this, a deep bass you feel in your chest, or nails on a chalkboard that make your skin crawl. Synesthesia simply amplifies the hidden connections the rest of us only glimpse. There are people who can smell sounds or taste emotions. In the rarest forms of synesthesia, the senses cross in astonishing ways. Some people smell the sound of a bell or taste emotions like sadness or joy as distinct flavors. A minor key might taste bitter laughter, might smell like citrus. These associations are consistent and automatic, hardwired into the brain's sensory map. They occur because regions responsible for processing different senses share unusually strong neural connections. While it may sound fantastical, brain scans confirm the overlap. Sound triggers activity in olfactory or gustatory areas. For synesthetes, the world is layered with invisible correspondences. Music becomes fragrance. Memory becomes flavor. Scientists studying them hope to understand how the brain binds sensations into one cohesive experience for all of us. In their perception lies a truth about ours. The senses are not separate instruments, but strings of the same vast, resonant chord. The brain can rewire itself. Blindness can make hearing sharper. When one sense fades, the brain doesn't leave the space empty, it reclaims it. In blind individuals, the visual cortex often repurposes itself to enhance hearing, touch, and memory. This neuroplasticity allows them to detect faint sounds or subtle textures that sighted people would miss. MRI scans show their brains activate visual regions when processing echoes or braille, effectively turning sight into sound or touch. This rewiring reveals that sensory areas aren't fixed. They're flexible networks shaped by need and experience. Deprivation becomes adaptation, proving that the brain is an artist of its own architecture. For those who lose vision, the world doesn't grow smaller, it changes shape. Space, sound, and vibration replace light, building a new kind of awareness. In every quiet footstep or distant echo, the blind brain paints an image, proving that perception is never limited, only transformed. Echolocation can be learned by humans through sound reflections. Though most famously used by bats and dolphins, humans can learn a version of echolocation too. Some blind individuals navigate by making soft clicking sounds with their tongues and interpreting the returning echoes. Over time, their brains become exquisitely sensitive to how sound bounces off surfaces, allowing them to perceive walls, doorways, trees, and even moving objects. Studies show their visual cortex activates during this process, as if converting echoes into mental imagery. With practice, people can estimate distance, texture, and size solely through reflected sound. The skill doesn't rely on superhuman hearing. It's pattern recognition amplified by attention. This ability reveals how adaptable the brain is. Deprived of sight, it turns sound into a new kind of vision. In darkness, echolocators describe their surroundings not as blackness, but as a landscape of returning whispers, a world drawn in vibration and air. People born blind often develop extraordinary spatial awareness. Without sight, navigation might seem impossible, yet many people born blind move through the world with astonishing grace. Their brains map space through echoes, airflow, and subtle pressure changes, transforming sound and touch into a living mental geometry. They memorize routes through rhythmic cues, the click of a cane, the hum of a corridor, the warmth of sunlight on one side of the face. MRI studies show that their hippocampus, the brain's navigation center, can become even more active than that of sighted individuals. This sharpened spatial intuition isn't merely compensation, it's mastery through adaptation. Blind travelers often describe perceiving open spaces or obstacles as sensations of presence rather than sight. Their orientation is not visual, but spatially felt. The brain, it seems, doesn't need eyes to understand the world. It simply finds new ways to see through silence. Your brain constantly merges information from all senses into one unified world. At every moment, billions of sensory signals stream into your brain. Vibrations, photons, chemical traces, touches, movements. Yet you never feel overwhelmed. Instead, your brain performs an astonishing act of synthesis, binding all these fragments into a single, coherent experience. Now, when you sip tea, you don't taste bitterness, feel warmth, and smell aroma as separate events. They fuse into one unified moment of perception. This merging is called multisensory integration, and it's what keeps reality seamless. The brain constantly cross-checks inputs, weighting whichever sense is most reliable at the time. When vision fades, Hearing sharpens when sound is unclear. Your eyes fill the gaps. Every second, your brain builds a complete world from incomplete data, a fluid illusion of stability and wholeness. What you call reality is this continuous act of blending, the artful harmony of all your senses singing in time. Virtual reality can fool your brain into believing you're somewhere else. Your brain doesn't distinguish strongly between real experience and convincing simulation. Virtual reality takes advantage of that, aligning visual, auditory, and motion cues so precisely that your brain accepts the illusion as real. Even when you know you're standing in a safe room, your body reacts to cliffs, movement, and height as if they were genuine. The sensory data overrides logic. Your heart rate spikes, your balance adjusts, your stomach flips. This is because perception is grounded not in truth, but in coherence. If the senses agree, the brain believes. Virtual reality researchers use this insight to treat phobias, train surgeons, and explore empathy, allowing people to experience perspectives far beyond their own. It's a reminder that your sense of place is flexible, built moment by moment inside your mind. Reality, it turns out, can be rewritten with enough sensory persuasion. When sight and sound conflict, your brain chooses whichever seems more plausible. If you watch a ventriloquist, you hear the puppet speak, though you know it's impossible. This illusion happens because your brain prioritizes whichever sense seems most trustworthy. Vision usually dominates, so the sound of the voice is relocated to the moving mouth you see. This is called the ventriloquist effect, and it's one of many examples of sensory compromise. The famous MC Girk effect shows it vividly. If you see someone's lips forming ga, but hear ba, your brain invents a middle ground, da. What you perceive is not what exists, but what fits best. The senses constantly negotiate, blending and bending reality into coherence. It's not deception, it's efficiency. Your brain's goal isn't accuracy, it's understanding. And in the fragile dance between eyes and ears, you realize that reality is something your mind constructs, choosing harmony over contradiction. You can feel motion even when perfectly still, a trick of sensory mismatch. When you sit in a stationary car and the vehicle beside you begins to roll, you may feel as if you are moving. This sensation, called vection, arises from a conflict between vision and balance. Your eyes report motion, but your vestibular system insists you're still. The brain reconciles the contradiction by believing the stronger signal, the one from sight. The result is a vivid illusion of movement, complete with physical sensations of swaying or acceleration. The same process powers virtual rides and flight simulators, which can make people feel motion while rooted in place. These mismatches reveal how dependent we are on multisensory agreement. The body is not wrong. It's interpreting the evidence as best it can. Every moment of stillness contains invisible movement. Even when you don't shift an inch, your brain can make the world glide quietly around you. Illusions happen because your brain is predicting reality, not just recording it. Your senses don't simply collect information, they forecast it. The brain is a prediction machine, constantly guessing what comes next and adjusting perception to match expectation. Illusions occur when those predictions overshoot. The Ames room makes people appear to grow or shrink because the brain assumes walls are square. Optical illusions like motion patterns or false color persist because your mind fills in gaps using its best model of the world. This strategy is usually flawless. It saves energy and makes perception instantaneous. But when the prediction fails, you glimpse the machinery behind reality. The world you experience isn't raw data, it's a constantly updated simulation, refined by memory, attention, and habit. Illusions don't show how easily you're fooled. They show how powerfully your brain strives to understand. You never see the world as it is, only as your mind expects it to be. Pain is real, but your brain can turn it off entirely in emergencies. In moments of crisis, people often report feeling no pain from even severe injuries. This phenomenon, called stress-induced analgesia, occurs when the brain floods the body with endorphins and endocannabinoids, natural chemicals that dull pain and sharpen focus. Evolution built this reflex to help us survive. There's no time to process agony while escaping danger. Soldiers, athletes, and accident victims often describe realizing they were injured only after safety returns. The pain wasn't absent, it was delayed. Once the brain senses that the threat has passed, the signals are allowed through, sometimes with full force. Pain, in essence, is not a direct message from the body, but a decision made by the brain, a balancing act between protection and performance. It reminds us that even our most primal sensations are under the mind's quiet command, turning itself numb when survival depends on it. The placebo effect can literally change how your senses perceive. When you believe something will help you, your brain begins to make it true. The placebo effect isn't just psychological. It can alter perception, pain thresholds, and even sensory processing. People given painkillers that contain no active ingredients show reduced activity in pain regions of the brain and increased release of endorphins. Placebos have been shown to change how wine tastes, how loud sound feels, even how warm the body senses itself to be. Expectation reshapes experience because the brain's predictive system updates reality based on belief. The placebo effect reveals that perception is not purely passive, it's participatory. You don't merely register the world, you help construct it, guided by anticipation and trust. In a sense, your mind can bend sensation with imagination alone, proof that belief itself is one of the body's most potent sensory tools. Some memories are stored with sensory tags that reawaken during dreams. When you dream, your brain revisits the sensory landscapes of your life, not abstractly, but through stored fragments of sight, sound, and texture. Neuroscientists call these sensory tags, patterns of neural activity that link memories to specific sensations. The scent of rain, the sound of laughter, the color of a particular sunset, all are encoded with emotion and place. During sleep, as the brain consolidates memories, these tags resurface and recombine into dream imagery. That's why dreams often feel vividly real, even when nonsensical. Your sensory cortex is partially active, replaying details from waking life. Sometimes, the faint smell of something near your bed or a distant noise weaves itself seamlessly into the dream's fabric. Memory, imagination, and perception blur. The senses don't rest when you sleep. They drift, remembering the world through echoes and light, stitching reality back together in the dark. Taste perception changes throughout the day depending on your body clock. Your sense of taste fluctuates with circadian rhythm, the internal clock that governs sleep, metabolism, and hormone release. In the morning, your tongue tends to be more sensitive to sweetness and less to bitterness. By evening, the pattern often reverses. These shifts likely evolved to optimize energy intake, craving sugar when you wake, avoiding excess calories as night falls. Even temperature and saliva chemistry vary by hour, subtly influencing flavor intensity. This is why coffee tastes different at dawn than it does after dinner, or why dessert may seem richer at night. Chefs and sommeliers sometimes use this knowledge to time tastings for maximum nuance. The body, it seems, is a living tide of chemistry, and flavor rides upon it. Every bite you take is filtered through time, not just by what you eat, but by when your senses awaken to taste it. Your body can sense changes in atmospheric pressure before a storm. Many people feel a heaviness or ache before the weather turns, a subtle awareness of falling barometric pressure. The body's tissues, especially in joints and sinuses, respond to these shifts in air pressure, expanding slightly as the atmosphere grows lighter. This can cause discomfort or fatigue in sensitive individuals, often before clouds appear. Even without conscious awareness, the inner ear and skin detect the change, altering balance and circulation. Animals rely on this sense acutely. Birds roost low, dogs grow restless, fish dive deeper. Humans too retain a vestige of this barometric sensitivity. Our ancestors used it to anticipate storms and shelter in time. When the air thickens and the wind holds its breath, your body may already know what's coming. A quiet dialogue between flesh and sky, reminding you that your senses still listen to the weather of the world. You can sense someone staring at you, and science is still unsure how. That uncanny feeling of being watched has puzzled researchers for decades. Some experiments suggest people can detect gaze direction with surprising accuracy, even without seeing who's looking. The leading theory is that subtle cues, faint sound, heat, or shifts in air pressure are subconsciously processed by the brain. Others think it's rooted in evolutionary vigilance. Those attuned to eyes upon them survived predators and rivals. Still, the effect persists under tightly controlled conditions, hinting at something deeper. Our brains may contain specialized networks for detecting attention itself, tuned to the emotional weight of being observed. The sensation might be your mind integrating countless small signals into one intuitive conclusion. Whatever the cause, the feeling is real enough to trigger physiological responses: heart rate, alertness, awareness. Sometimes, perhaps, the body simply knows before the eyes do that it's become the center of another's gaze. Some people can feel weather changes in their joints. Many who live with arthritis or old injuries report aches before rain, and science gives this folklore weight. Changes in barometric pressure can subtly alter joint fluid and tissue, causing nerves to signal discomfort. Lower pressure lets tissue expand slightly, increasing sensitivity in inflamed areas. Humidity and temperature shifts can intensify the effect, creating a kind of internal weather forecast. Not everyone feels it, but those who do often sense storms hours before they arrive. The phenomenon reminds us that our bodies are not isolated from the sky. They are barometers of flesh, resonating with the atmosphere's invisible tides. Every ache is a whisper of changing air, a message written in joint and bone. The weather doesn't just happen around us, it moves through us, a dialogue between human biology and the shifting pressure of the Earth's breath. Sound can change how food tastes. In a quiet experiment, people rated the same piece of chocolate differently, depending on background sound. High-pitched tones made it seem sweeter, low ones made it feel more bitter. This cross-sensory phenomenon, known as sonic seasoning, shows that hearing influences taste perception. Restaurants now design ambient soundscapes to enhance dining experiences. Soft, bright music for desserts, deeper tones for savory meals. The effect is psychological yet measurable. Sound alters expectation, and expectation alters flavor. Even crunchiness depends on sound. Potato chips seem fresher when they sound crisp. Your brain merges these cues automatically, blending hearing and taste into a unified impression. Eating, it seems, is not just gustatory, it's auditory too. Every bite carries not only flavor but resonance, proving that the senses don't work in isolation. You don't simply taste food, you taste the music of the moment. Color can influence how something feels or smells. Your perception of texture and aroma is subtly shaped by color. People describe drinks in red cups as warmer, heavier, or sweeter than the same liquid in blue ones. Yellow packaging can make food seem fresher, while green evokes naturalness and calm. Even scents shift with color context. A neutral perfume may seem floral when paired with pink, or woody when paired with brown. The brain doesn't separate sight and smell, it synthesizes them, creating associations that feel instinctive. These cross-modal correspondences likely evolved from environmental patterns. Ripe fruit is brightly colored and sweet, spoiled food, dull and bitter. Designers, chefs, and perfumers now use color to steer perception, guiding emotion through light and hue. The truth is simple and strange. Your eyes can change what your nose and hands feel, weaving the senses together into one emotional language of color. The smell of coffee can improve alertness even without drinking it. The aroma of coffee alone can stimulate the brain's arousal centers, increasing alertness and improving reaction time. Studies show that simply inhaling the scent activates regions associated with attention and wakefulness. In one experiment, students exposed to coffee aroma performed better on cognitive tests, despite consuming no caffeine. The effect seems to arise from learned association. Over time, the brain links the smell with the physiological energy of drinking it. The scent becomes a signal, preparing the body for action. This kind of sensory conditioning is powerful. Your mind responds not only to chemistry, but to meaning. The smell of coffee at dawn, the rustle of pages, the faint hum of the day beginning, all are cues that awaken more than the senses. They awaken habit, memory, and the subtle anticipation of being alive in motion once more. Certain sounds can make you shiver, a sensory response called frisson. A sudden swell of music, a perfect harmony, or a haunting voice can send tingles cascading down your spine, a phenomenon called frisson. It's caused by the brain's reward system releasing dopamine in response to emotional tension and surprise. When music defies your expectation, a pause, a key change, a sudden crescendo, your brain floods with pleasure, translating emotion into physical sensation. This reaction isn't limited to music, poetry, film, or even a beautiful idea can trigger it. Frisson is a sensory mirror of awe, a bodily echo of wonder. The hairs rise, the breath catches, and for a fleeting second, the boundaries between thought and feeling dissolve. It's as if your entire nervous system applauds what your mind cannot articulate. Frisson reminds us that the senses are emotional instruments, tuned to the invisible frequency of meaning. ASMR triggers real physical tingles through auditory stimulation. ASMR, Autonomous Sensory Meridian Response, is the gentle tingling sensation many people feel from soft sounds like whispering, tapping, or brushing. These stimuli activate neural circuits linked to relaxation and pleasure, producing waves of calm that ripple from the scalp down the spine. Brain scans reveal that ASMR increases activity in areas tied to emotional comfort and bonding, similar to those activated during affectionate touch. For some, it's a tool for sleep. For others, a form of meditation. The effect relies on hypersensitivity to microsounds, the intimacy of detail, the nearness of voice. In a noisy world, ASMR offers a rare kind of quietness, attention slowed until perception itself becomes soothing. It's the science of calm disguised as sensation, proof that even the faintest whisper can stir the deepest parts of our nervous system into peace. Even silence has a sound, the faint hum of your own body. In absolute quiet, most people begin to hear a subtle noise, the hiss of blood moving through the ears, the pulse of the heart, the murmur of muscles contracting. True silence doesn't exist for living beings. Our bodies are symphonies of motion. Anechoic chambers, Rooms that absorb all external sound often make visitors uneasy because the brain expects environmental noise. Deprived of it, awareness turns inward, amplifying the body's own rhythms. What you hear in silence is yourself, the ongoing machinery of life. It's a reminder that hearing is not external alone. It's internal perception too. When the world grows still, the hum of being becomes audible, steady and small but infinite in meaning. Silence, then, is not absence, it's intimacy. The sound of existence reminding you that you are, at every moment, profoundly alive. Sleep alters your senses. Your brain filters sound differently to protect rest. While you sleep, your brain doesn't shut down your senses, it adjusts them. The auditory system remains partially active, monitoring the environment for danger, but filters out harmless sounds. Familiar noises, a fan, soft breathing, distant traffic, fade into background. Sudden or unfamiliar ones, like a door creak, can jolt you awake. This filtering happens in the thalamus, which acts as a sensory gatekeeper. Even smell sensitivity changes. Your nose is less responsive during deep sleep, while touch becomes subdued. Yet during dreams, sensory memory reawakens internally, replaying sensations in vivid detail. Sleep isn't sensory absence, it's sensory reorganization, a nightly recalibration of the mind's alertness. The world doesn't vanish when you sleep. It quiets, rearranged into safety and rhythm. Your body listens gently, guarding your rest while allowing consciousness to drift peacefully through its private realm of dreams. Your perception of reality is a symphony your senses compose together. Every sound you hear, every color you see, every breath you take is part of a grand orchestration, your senses performing in harmony. Each moment, light, vibration, pressure, and chemistry converge into a single experience, the world as you perceive it. But no two symphonies are the same. Each brain arranges the notes differently, shaped by memory, emotion, and biology. What you call reality is a private composition, endlessly adaptive, endlessly new. The senses are not mere instruments, they're translators between matter and meaning, turning waves and particles into feeling and thought. Even now, as you listen, your body and mind are blending information into music, the music of existence itself. The senses are how the universe becomes self-aware, a harmony of perception unfolding within you. And in that quiet understanding lies the most beautiful truth. You are the melody that reality hums through. And now, as the final echoes of tonight's journey fade, let your awareness rest. You've wandered through the quiet miracles that shape your every waking moment, the flicker of light that becomes color, the breath of air that becomes sound, the warmth that becomes touch. Your senses are not simple instruments. They are the threads that weave the fabric of reality. They translate the invisible into the intimate, turning waves, particles, and molecules into the living poetry of experience. Every sound you've ever heard, every taste you've ever loved, every scent that has ever carried you back through memory, all of them are the language your body uses to speak with the universe. Even now, as you lie still, those senses continue their gentle work. Your skin feels the air around you. Your ears listen to the hush of the room. Your heartbeat murmurs beneath the quiet. The body never stops sensing. It only shifts its attention, softening from the outer world into the inner one. In this calm, you can feel what perception truly is. Not a flood of data, but a symphony of meaning, tuned by emotion and memory. Your brain doesn't just record life, it composes it, moment by moment, turning sensation into awareness. And when you sleep, that awareness drifts like mist, carrying fragments of touch and sound into dreams, a slow rehearsal of consciousness itself. So breathe deeply now. Let the world dissolve into gentle hums and distant echoes. Let your mind become lighter, quieter, softer. The senses that kept you awake will guide you inward into a quieter kind of perception where sound becomes thought and thought becomes rest. If you've enjoyed this sleepy journey through science, the wonder of the senses, the music of perception, you can subscribe to the channel and join us again for the next story. There are countless worlds still waiting, deep oceans, distant stars, the strange physics of the mind. But for now, you've reached the still point, where curiosity meets calm. Close your eyes, let go of the day, and drift, slowly, into that soft, infinite silence, where all senses fade, and only peace remains. Good night.